Hello everyone, today we discuss contest 17. I would say it's not that hard, so it was implementational heavy, so a lot of problems require some implementation. Starting like from the first problem, uh, every problem requires to write a lot of code, more than usual. And in last problems we have some geometry, so I decided it would be nice to have some geometry at least, so we don't have it usually. But today at least we have two problems, very similar problems actually. My code is almost the same. So today last three problems are like three problems from what's called Helvetic contest. So there is a Helvetic coding contest which kind of usually works like this. You have for each problem you have three copies, and like easy, medium, and hard. And you solve one problem, they give you another one. So that's what. So initially I found this first problem as some easy problem for this problem set, but then I decided why not take these two problems as well. And it turns out these two problems are harder, but they're actually pretty much the same. So I use kind of the same code for G and H. The change is not that crucial. So let's go. So we will start to discuss all the problems. We discussed all from the first one to the last one, like usual. I pre-recorded myself this time. It took a little bit more than 1 hour. Okay, hour and 12. Okay, so it took a little bit more than 1 hour, but we will speed up myself. So we spend less time looking how slow I'm solving. Let's go. So problem number one, very simple problem. You need to just implement what's written in the problem statement, but again, it's implementational heavy problem. You need to implement all this stuff. So just carefully implement what's given. So you're given some amount of ice creams, and some people are coming, and if some people bring you ice creams, some people request ice creams. If person brings you ice cream, you just increase your counter here. If it requests ice cream, you check if you have enough, you give it. If not, then this person is sad, or what is it? In distress. Okay, so this person will be in distress. This counter B counts how many persons are in distress. Pretty straightforward, but still, again, it's like 20 lines of code. It's more than we usually have in the first problem, but all this code is kind of very technical. Yeah, so no interesting idea, nothing basically to invent here. Yeah, you just need to carefully implement what need to be implemented. And again, it's programming competition. Yes, you need to be ready to implement stuff. Yeah, so if you have problem which requires only implementation, it's sometimes it's kind of not very fun to do it. Yeah, it's much more fun to solve some tricky problem with some interesting ideas. Yes, but if you just need to implement stuff, no, just implement stuff and go to the next problem. This time we have a lot of problems when we just need to implement stuff. It also happens. Sometimes you have a contest which only requires implementation, but still it's a good training of implementation. Yes, next time we'll have some more problem when you have some ideas. Yes, here we don't have. Second problem, again, pretty straightforward. Here you need to think again what you need to calculate, but problem itself is pretty straightforward. So you're given a string, some space are empty, some space are blocked, and you can jump at most k cells to the right. You need to check if it's possible to jump from the left cell to the right cell. And I do it like this. So I go left to right, I find empty cells, and I check if the distance between this cell and the previous cell is more than k, then it's impossible. Yeah, that's it. It's very simple code actually. Yes. Again, another thing that you need to train is to implement simple problems in a simple way, right? So if you overcomplicate stuff here, then in more difficult problem, you will not be able to implement it. Yes, so try to implement it in a simple way. So if problem is simple, try to find the simplest way to implement it. So next time you spend less time doing it. Let's actually try to look at your solutions at this point. Did you have any problems with first two problems? Okay, some of you actually keepers. Okay. What happened to the first problem? How can you What can go wrong in the first problem? I disabled the enable management. One more time. What can go wrong in the first problem? Very nice variable names. Okay, that's very meaningful, but again, it's pretty hard to do it in real context. Don't do it in real context, please. Just call them 1-2 letters, 3 at most. Okay. Okay, with a sign ice cream. Okay, if sign is plus plus. If not, if I have greater or equal, should be yes. No. If ice cream asks more than I have, then in distress. If not, subtract ice cream. Looks okay. Looks not bad. So we didn't initialize these variables. Okay, this is 0. This we will read. This one we will read. This one we will read. Char sign. I'm not sure what's happening with chars here actually. If you read one char, will it read it from the next one? Will maybe it will read just a space. Okay, no, it will not pass the first test. You have just integer flows. Okay, makes sense. Integer flow is common problem. Again, what I do now, so I do here. See here in the top. Let me show you. So in this season, I'm doing it like this. So I am so tired of getting integer overflows problems. So this season I'm doing all integers 64 bits. Just so do not think about 32-bit integers at all. I was thinking of making everything 128-bit, but again, not every function implemented for this type. So every function is implemented for 64 bits. So I just get like this. And if I need something extra, then I use this type. Okay, that's okay. That makes sense. So that's mistake everybody make at some point. That's not a big deal. Okay. Problem C. Yeah. Problem C. Again, they just tell you what you need to do. So you have field 4x4, and you need to check if there exists, if it's possible to put another cross. So you have 3 crosses in a row. Many ways to do it. For example, what you can do, again, it's 4x4 grid. Yeah, you can check all possible moves. So there are 16 possible moves. Yeah. So you make the move, and now you need to check if there exist 3 crosses in a row. You just check every triples of consecutive positions. So it may be vertical, horizontal, diagonal like this, diagonal like this. Just check all possible triples. Not that many of them. You just check all of them, and you're done. I did it a little bit different, so I don't make the move. I just check all the triples and check if I can make this triple. So if I have a triple and it has 2 crosses and empty space in any configuration, yes, something like this, yeah. So if I have anything like this, then I said yes. Okay, so I check all possible triples and check if it contains 2 crosses and empty space. That's it. That's my solution. But now you need to carefully implement it. Okay, and it's not that difficult actually. So if you do it a couple of times, you do it. Okay, let me. Okay, here I check in only vertical lines. Here I hesitated for a second. I was thinking if I need to copy this code just 4 times. So again, we have 4 possible directions. Yes, I could copy this code 4 times. It will just work, but I decided it's more for educational reasons. I decided I would, instead of copying this code 4 times, I would do it more carefully. So what I'm doing, it's how I normally implement programs like this. I make basically array of directions. So I will have array of 4 different directions. 4 4 directions. Yes. So again, every combination of dx dy give you some direction. It's basically vector. If you don't know vector algebra, it doesn't matter. Yeah. So it's basically these two numbers tell you in which direction you move. Yeah. So you may move in vertical, horizontal, or diagonal here, diagonal there. Yeah. And now I will just check all the directions and make this code universal. So I make this code so it works for any direction. Okay, let's skip a little. Oh, yep, okay. So what I'm doing, I iterate all possible directions. Then I choose some starting point. Yeah. Then I need to check if from this starting point I can build 3 units in this direction. Something like this. Yeah. So I find the start of the line will be here, the end of the line will be here, and I just check if the end of the line is inside the field. Yeah. If it is, then I check this line. So I check this line, I go in this direction, go in this direction. Oh, this should be dy, this one should be dy. I will fix it. Yeah, and then so I go, okay, so here I choose the direction, I choose the starting point. Yes, see. So here I check all 3 elements in the direction. K equals 3. Yeah, for simplicity. So I check all 3 elements in this direction, and then in the end I just check if I have k minus 1 to 2 x's and no o's. No, how called it? This o's. Then yes. No, that's the whole code. So again, now I'm looking for the mistake. Okay, let's watch me how fast I can find this stupid mistake. So you see, I just read the whole code. It's small code. It's easier just to read it once. Yeah. So I didn't test. I have test, but I didn't investigate what's happening in this specific test. I just read the whole code and check that it does what I expected to do. Yeah. And just find this mistake. So here you see. So after some time you're doing this, you just see this. You see it's just non-symmetric here. Yeah. So it should be dx dy, dx dy. Yes. So it would be ij, dx dy. Yes. It should be also dx dy. Yeah. Yep. So that's it. That was the whole mistake. Let's see how you implemented it actually. Okay, but you didn't solve the problem. You didn't solve it. Why did you solve it? Absolve it. It's pretty simple problem actually. So you need to be able to solve these problems in reasonable time. So just spend some time solving problems like this. After you solve like 10, 20, 100 problems like this, you will do it just without thinking. You just read the problem and immediately write the code. Okay, maybe not immediately, but fast enough. Yeah. So who did okay, Konstantinos had a hard time. Okay. No, okay, let's find one. Okay, so you tried to actually copy your code a couple of times. Okay. You see, that's why I'm not doing it like this. Yes, so I could copy the code 4 times. You actually don't do it 4 times. You copy it too many times. Okay, copying 4 times, it should be okay. Copying 12 times, so how many times you do? You just do it for every for every direction. So, but you have 4 directions. What? You find empty space and you check if you put here. Then in every direction, there are 3 possible ways how you can build, yes? So you have 12 combinations here. Okay. Okay, we learned something new. So you don't do it like this. You see, that's the example of just too complicated implementation for very simple problem. Yes, try to implement in a very simple way, yeah, not like this. So if you have 100 lines of code, that's very easy to make mistake. Here you see, I don't know where is mistake. Anywhere could be, yeah. Any of these copy pasted lines could be mistaken, yeah. We will not look for mistake. Let's go to the next problem. Again. Are you seeing this chat? Yes, I'm seeing the chat. What? Any questions? Yeah? You had any questions? I didn't hear anyone. Yes, I see the chat. You can ask questions in the chat, or you can ask them in voice, whatever you like. Yes. So let's go to problem D. Problem D. Oh, it's another, again, pretty much everything written in the problem statement. Yes. What's happening in problem D? You have some passwords. Basically, you have strings. Yes. At most 100 characters. Yes. Very nice problem statement here. And you try these strings as passwords. Yeah. And you try them in decreasing order of their length, in non-decreasing order of their length. So it starts from short passwords, then longer. And you need to find the minimal and maximal time it may take to guess the password. Yep. Yeah, and also every k times, if you try wrong password, you need to wait for 5 seconds. Just okay. Nothing that difficult in this problem. So what again? Again, if you read the problem statement carefully and also read the notes in the answer, let me show you. In the end of the problem, there are some notes. Basically, carefully explain what's happening in the examples, and basically they spoil you the whole solution. So what's happening in this solution? So what's happening here? So you have strings, you try them in increasing order by the length. Yeah. So if this is your password, then before it, so there are passwords which are strictly shorter. So all the passwords which are strictly shorter, you will definitely try before this. Yeah. And also there are passwords which have the same length. Yeah. Out of these passwords, you might try them in any order. So in the best case, you will take your password as the first one. In the worst case, you will take it as the last one. Yeah. So in the best way, you need to try this many times. In the worst case, you need to try this many times. That's it. And now you just need to carefully check, if you try it this many times, how many times you need to wait for 5 seconds. I actually do it some strange way. You could do it much easier. I do it like this for some reason. I don't know. It's like how my brain worked. So I count. No, because you need to know only the length of the string. I decided I will do counters. I will count how many strings for each length I have. That's actually overkill. You can do it much easier. Yeah. So here, so this is my minimum. So I count all the strings which have size less than mine. And this is my maximum. I count strings of the size less or equal than mine. This should be equal, less or equal, yes. And now I will just implement function calc, which will tell me how much time I spend if I try this many passwords. Okay. So if I try this many passwords, I need to spend 5 seconds every time I try key passwords. So last try is correct. Yeah. So I make x minus 1 incorrect tries, and each k of them will give me 5 seconds of delay. Yeah. So that's basically the formula which gives me how much time I wait for 5 seconds if I try x passwords. Yeah. That's basically it. And here I submit it, and I get wrong answer test number 6. Can you find the mistake in this program? Okay, let me show you the whole program. Actually, mistake is not here. Okay. My submissions, my submissions. Copy. Let's copy it here. Actually, mistake is in this formula. Can you find the mistake? It's almost correct. Let me look. So what I tried to do, so again, if you make X tries, yeah, so if you try, so if you try X different passwords, so last try is correct, yeah, so I have X minus 1 incorrect tries, yeah, so you group them by K, last one, so, and every time, so this K, yeah, after every K incorrect tries, here you need to wait. Here wait, you wait here, you wait here. So total number of tries you need to do is equal to, so I spent 5 seconds for each X minus 1 divided by K floor, yeah? No, floor, not sale, yes, because last time, so if I make, here I make less than K tries, so I don't need to spend it. So that's the formula. Now find mistake in the program. Spoiler, formula is correct. Program is incorrect. Can you see the mistake? No, come on, think. This line is incorrect. So this line doesn't do what expected to do. I expected to do this. It doesn't. It does something different. Should have worked. It's right. Yes. So this formula actually does following. So it does 5 multiplied by x minus 1, then divided by k, and then floor of this. It's not the same. Yes. So you need to put this in the brackets like this. Yes. Or you can move multiply it by 5 to the right like this. So it first divides, then multiplies. Good, good. So that's the mistake. So now let's watch me finding this mistake. So I know I have wrong answer test number 6. Yes, multiplication and division have the same priority. Yeah. So they apply it left to right in this order. Yeah. Normally it's okay. Normally it's actually normally that's what you want to do. You first multiply, then divide. Yeah. Almost always you need to first multiply, then divide. But here, okay, so okay. I have no idea what's happening here. Okay. Again, I read the whole code, try to find any mistake, but the code is much easier than in the previous problem, actually. It's kind of hard to make mistake here. So I think maybe I misread something in the problem statement. So again, I read these notes. I see that I understand the problem correctly. Okay. Try to read it once again. That's okay. So no tricks here. No tricks here. Here I'm panicking a little because I have no idea what's going on. So code is too simple to make mistakes. You see, sometimes you have very simple code which just doesn't work. Yeah. When you have a long code, you need to you can investigate, you can try, you can do something stress test. But if code is really simple, it's always stressful to find the mistake because okay, finally yes, okay. Okay. Again, and this line is so simple. You don't expect you have problems here, right? So again, so that's the lesson for you. So sometimes the bug is hidden in very strange place. Sometimes the bug hidden in the input. Sometimes I read the input incorrectly, and have mistake there. Be careful. Be careful. Try. Okay. So you know the code doesn't work. So there should be some mistake. Just try carefully scan all the code. Find the mistake. It's okay. Okay. Problem E. Problem E is a strange problem. I believe it can be solved in log n time. But they give you, so constraints are pretty small here. So numbers are up to 10,000. So I'm not sure why. I believe we can solve this problem in log n time, but you don't have to. So you can just do BFS. Yeah. So if you have, so again, you have numbers up to 10,000. And it kind of makes sense. You never need very large numbers in the middle. Yeah. So all intermediate numbers are also small. So let's just build a graph on 10,000 vertices and find the shortest path. Why not? I believe this is the easiest solution here. There should be some mathematical solution also. But again, when I need to choose between BFS and some interesting mathematical solution, I would always choose BFS, because BFS, that's the simple algorithm. You know how to implement it. Yes, why not? It's much easier to implement BFS than find mistake in your math. Yeah. So what I'm doing here, okay, I made mistake in BFS here. You see, I make pretty straightforward BFS. So I have this size. So I will build graph of size 2 multiplied by maximum of these values. So you never get elements more than twice of your numbers. That's for sure. Yes. And here I just make two moves. So from each vertex you have two transitions, to x multiplied by 2 and to x minus 1. If this vertex exists, I make this transition, update my BFS, update the result. That's it. That's the whole code. Yeah. Pretty simple BFS. Oh, then I believe there is some logarithmic solution, but I decided if I can do it using BFS, why not? Yes. Again, it's much easier to implement BFS than to think. When you're thinking, you may make mistake. It's hard to make mistake in BFS. Okay, it will just pass. So let's watch your solutions. Okay, let's watch your solutions. What is E? Okay, I would usually use pen and paper for things like this. It's much faster to write this thing on paper than to here. Oh, is that simple? Yes, if it's greater, you just take minuses. Yes, why not? Okay, so you see the minimum, you find the minimal power of 2 you need to do. So you need to do this many multiplies. Okay. Okay, that's the remainder. So you need to subtract this remainder now. Okay, and the maximum you can subtract is this. Okay, makes sense. So you subtract these ones and you have some remainder and you do it just. No, remainder is when you subtract. You need how many times you do minus ones. Yes. And this mx is what's left. Yes, I see. Good. Yeah, no. It's good for you. In some another contest, it would be the only correct solution. Yes, if they give you some big numbers here, that would be the correct solution, and my will get time limit. Yeah, but again, you need to pay attention to constraints and find the solution for the given constraints, not for the possible maximum constraints. Yes, only for given constraints. So, but good for you. No, good solution. Okay, and now we move to the last part of this contest. We have 3 problems about zombie contamination. I don't know why. I know what was the story. I think the zombies was the theme of this whole Helvetic contest. We had already some contest, some problems about zombies. I don't remember this season or previous season. Maybe it was the previous season. We already had some problems when you had zombie brains as some trees, and you need to combine these trees, something like this. Maybe it was last year. So here is another some zombie themed problems. What we have this time? So we have some, in the first problem, we just have a rectangle, and for every cell, we know how many corners are inside these rectangles. And for the first problem, it's pretty simple. So what's happening first problem? So if you have some, can I make this? No, I don't want to draw this. Up, space, like this. Up, and thickness. Will make it. Oh, nice. Oh, okay. So if you have some rectangle, then what will happen? Every cell in the inside will have all four corners. Yeah. So you have some rectangle of fours. Then here on the sides you have twos, and here on the corners you have ones. Yeah. Everything else is zero. You have zeros everywhere else. Yeah. So that's what you need to find. So you need to find this rectangle of fours, basically. That's your rectangle. And now you just need to check that it corresponds to this picture. So given picture corresponds to this. Yeah. So all these numbers are twos, all these numbers are twos. Here you have twos, here you have twos, and these corners are ones. So you just need to check this. Okay. Again, implementation will have a problem. Yes, you need to implement this stuff carefully, without mistakes. So how I do it? Let me see. Okay, so here I find the borders of my rectangle. Yeah, so I just find the bounding box of all fours, and just okay, if I didn't find any four, I just know. Yeah, and now I just need to check that my picture is correct. How I do it? I will do it like this. I will draw my picture and then compare this picture and that picture. Yeah. So basically I do it like, okay. I just do it like explained here. So I take all the cells. Then for each cell, I check all four corners. So these two loops, these two for loops, you see, they check all four corners. And I check if the corner is inside, I increase the counter. Yeah, so this counter counts how many corners of this square are inside the rectangle. And then I just check if I have the correct name. Like this. So basically, I find this rectangle of fours and then check if the picture produced by this rectangle is equal to what we have in the input. No, like this. Many ways to do it. I did it like this. Let's see how you did actually. Ah, you didn't. Ah, you upsolved it. Okay. No, basically the same. Good. Okay, but you check it like this. Okay. Nice. So that's the first problem from the cycle. Again, only implementation. No interesting ideas happening here actually, just implementation. No, sorry about this actually. So I don't like when contest is purely about implementation, but again, it's random contest. I didn't choose the problems because of the implementation. Just sometimes random gives you implementation heavy contest. again, it's training. Yes, in training, sometimes you need to train yourself to do something which is not very pleasant. Yeah, like implementing this stupid stuff. But again, it teaches you how to implement these problems like this in a simple way and do it fast enough. Yeah, so that's what we train. That's what we train. Yes, we train implementing heavy stuff in a simple way, fast. Yeah. Okay. And now we have two difficult problems. Actually, G and H, they are actually almost the same. So I copied the uh, almost whole code from problem G I used in problem H. What we have? So we have now. Okay, so what was my idea? My idea was like this. So if you look at any corner, next to this corner, because it's convex polygon, next to this corner always have one. Yeah. So there's always one of the corners which have only one of the cells which has only one corner covered by this polygon. Yeah. And moreover, for this one, one has two neighbors which are 0. So we have 1, 0, 0. Then this corner must be in the polygon. And you have simple thing here. You have 1, you have 0, 0. So this corner must be in the polygon. And you have the same thing here. So sometimes you have separate ones. So it's for the same corner, and this one for the same corner. And for this corner, you have this 1, 0, 0. So what I will be doing, I will look for these combinations like 1, 0, 0. And every such combination will give me a corner of the polygon. It actually turns to be not true. Not all of them give me corners of polygon. For example, here, this 1, 0, 0, give me some point in the middle. But I will just remove this point. I thought I will just remove this point, and that's okay. It turns out that that's not it. So there may be even more tricky situation when you have. So you have, let's say something like, let's say from here you have like to here, like pop, something like this. Then this point will be 1, this point will be 0, this will be 0. But this corner is not vertex of the polygon. So actually this method produces not only corners of the polygon, but also some points inside the polygon. So my updated solution does the following. I find all these, again, I find all these combinations like 1, 0, 0, find all these combinations. So if I have 1, 0, 0, I know that this corner is inside the polygon. It's either the corner of the polygon or some point inside the polygon. So I just take all these points and find the convex hull using standard convex hull algorithm. Again, convex hull is a little bit, okay, it's not the easiest thing in the world, yes, but it's out of all computational geometry, it's pretty simple algorithm, you say. So, so if you need to study computational geometry, that's like one of the first algorithms, like real algorithms you need to implement, yes. So you need to implement all the basics like line intersections, segment intersections, stuff like this. Then you probably need to implement checking if the point is inside the polygon or outside, yes. And then you have convex hull. Yeah, convex hull, one of the first algorithms you learn when you learn computational geometry. Yep. So normally, if I would do it from the beginning, I would just copy my geometry library here, yeah, and use convex hull from my library. But I decided I will do it from scratch. So I spent how much time? Almost an hour implementing all the geometry. Okay, it's not only geometry, actually a lot of stuff here, implementational heavy. So here I'm just thinking. Here I also implement. So here I implement simple things. So here I implement what I told you. Yeah. So here I take in all all the cells, check if cell contains 1, look at 2 neighbors. If they both zeros, then I add the corresponding corner to my set. So here I will put all potential corners of my polygon. Yeah. So this array P will contain all the candidates to be corners of the polygon. Now you need to sort. You need to sort because you need to find the lexicographically minimal coordinate. Okay, and here I push. Coordinates are different, so coordinates actually come from bottom to top. So you need to invert the coordinate y. Okay, so a lot of non-important stuff happening in this problem. But again, it's you're programmers. Yes, you need to sometimes do some strange things. Okay, here I decide I need to do not these coordinates I and j, but normal coordinates. So I need to transform these coordinates to that coordinates. Okay, I decided to do it here. So that's how I translate my matrix coordinates to like geometry coordinates, you see. Okay. I don't like this problem that much, but it's not that terrible. Yes, we actually had much more terrible problems in this series, but it's okay problem. Again, I thought it could be solved easier. That's why I spent too much time. If I initially thought I need a convex hull, I would just start from it. It would make actually things easier. Okay, so again, what I normally do, I implemented some code, I check what's happening here, yeah? So now I added all the candidates and see the candidates are incorrect. So this sequence doesn't make sense. So I try to find mistake. Mistake was here, I believe. So this should be not minuses, but pluses. Yes. Okay, now it looks more correct. So here is the list of all my candidates. You see? So for this picture, I have these 5 elements. Okay, so 5 elements, including again this middle point. Yeah, again, so here are these 5 points, including this middle point. Okay, now I will do some strange thing. I will try to remove these middle points because I thought it's the only mistake. Yeah. Here I sort them by the angle. Not by angle. So here. So what I will do, I will sort all the points by the angle because I found again how you do convex hull. It's not convex hull yet, but it will be in the show. So you find the leftmost lowest point, like this point. Then starting from this point, you sort everything by the angle. Chuk, chuk, chuk. Yeah. Normally I would do it in counterclockwise, but they asked for clockwise, so I do it in this direction. Yeah. And then you go in this order with stack and like remove the points which have different direction. Yeah. Okay, so that's what I'm basically doing here. I first sort all the points by x. Okay, I'm doing it like this in integers. That's how I always implement it, so I don't have any problems with floating point numbers. Yeah. So I calculate the cross product and see if X cross product is negative. That's it. So that's how you sort by the angle. Okay. Yes, in the near future, this algorithm will transform to the normal convex hull. I'm just trying to cheat here. I will in the end I will make the normal convex hull. Convex hull will remove all the middle points, create all the non-important points. So it will remove everything except the corners of the polygon. Okay, so I'm doing some strange thing here. It's actually taking too much time. Okay. I decide to so here I thought I could remove only points in the middle. So here what I'm doing here, see? So I check if point's okay, if I can remove it. So if the cross product of 3 consecutive points is 0, then middle point may be removed. So I did this and got luckily, judges are kind enough to give me the last example when the situation happens. So situation like this happens in the last example, luckily. Yeah. So here. So one of these points is actually not in the, not on the side of the polygon, but it's in the middle of the polygon. Okay, so we need to remove it carefully. So here, okay, so here I'm trying to understand what's going on. Pop, 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 pop. Okay, and here I said, okay, we need convex hull. Let's remove everything. Okay, so that's no normal Graham algorithm. Okay, let's back. Oh, can I go back? Can we go back? No, no. Oh, yeah, that's that. Okay, like almost. Okay. It's already speed up solution. I don't know why I'm so slow. So okay, let me show it here. My submissions. Okay, I made a lot of mistakes on the way. Actually, you will see. So that's the Graham algorithm. Yeah. So what you do? You have your points already sorted in order. Yeah. So I push the last point in the end, so I kind of have the full cycle, including the. So first point is the same as the last point. Yeah. And here so this should be minus, so it should be, it doesn't matter. So here I pop, so I have the stack, so this is my stack. I pop all the points if they have incorrect sign of the vector product. So if vector product is correct sign, I break from this while. If it is incorrect, I pop it and continue. So this while loop pops everything which is which is definitely inside the polygon. Yeah. And then I push the last point here. So that's basically the Graham algorithm. It's -1 should be not -1, but it doesn't matter. I will fix it. Here I have a constant test 4. I think a little. Okay, so this -1 should not be here. Pop, pop. So I try all the points, including the last points once again. Yeah. So I start and finish in the same point. So in the end, I pop this last point because it is always in the end. So I don't repeat it, I pop it. And here I get wrong answer test 6. Oh no, 5. Okay. Okay, so now it's more complicated mistake. Okay. That's because I didn't use my normal convex hull algorithm. Okay, let's lecture time. Short lecture about convex hulls. How you find convex hulls? You do it like this, normally. Yeah. So you have your points. You find, okay, so these are your points. So you find the leftmost point out of all this. So again, minimal lexicographic, it doesn't matter. So you find some point here. Now you sort everything by the angle. The problem is sometimes you have several points on the same angle. So you have here, you have several points on the same angle. Yeah. So you need to sort them somehow. So you sort them by the distance. So that's how normal Graham algorithms work. So I sort points by angle and then by the distance. The only problem is with the corners here. So with these sides. So for one side, for the first side, you need to do it in increasing order. And for the last side, you need to do it in decreasing order. There's actually another algorithm. I don't remember the name, Andrew's algorithm. So when you sort points just by x coordinate, and then you do the upward part of the convex hull, and then separately do the bottom part of the convex hull. In this algorithm, okay, in any algorithm there are some tricky cases, but again, that's just technical difficulties, careful implementation of the convex hull. I didn't do it for a long time, so I screwed up a couple of times. Let's see. So here, yeah. So what I need to do here, I need to sort not only by angle, but also by distance. So if angle is the same, if cross product is 0, I sort by distance. Distance, I need function distance. Again, that's what you normally have in your geometry library, yes? Again, I look here, I sort by angle and then sort by distance. Yeah. Now, in the end, you need to reverse the last line. So I always sort in increasing order, like this. Yeah, but this last line need to be sorted in decreasing order. It's kind of important because you want to finish here, and then you want to finish here. You want these 2 points. So this point must be the last out of all these points, and this point must be the first of these points. Oh, yeah, it's not here. Again, it's very default thing. That's how you normally implement convex hull if you carefully implement convex hull. Yes, if you don't want to cheat like me. Again, so this code just reverses this last section. Yeah. So I take all elements equal to the last one with the same angle as the last one, and just reverse this last section. And everything else is the same. So this part is the same. So this part didn't change. Okay, so that's it. That's okay. Let's look at the final solution. How much time I spent here? From 37 to 11. It's like 20. It's more than half an hour here. Okay. Not terrible, but not great. Okay. Again, so that's the full solution with all homebrew little bit geometry. So that's out of all geometry, what I need cross product and I need distance basically. Yeah. So it's square of the distance. Yeah, like this. Okay, here I find all interesting points, put them, sort them. I actually need this sort only to find the minimal lexicographically. I could just find minimum and put it in the first position, but who cares? I also remove duplicates. Now, I sort everything by the angle here. Looking at cross product, I know how they correspond, yes? And if they have the same angle, by the distance. Yeah. Then I take the last section and reverse it because I want this last section in decreasing order of distance. So everything else is increasing by distance and the last section is decreasing by distance. And now I do this stack tricks. So when I walk along this along this, basically you build non-convex. So you build some non-intersecting broken line and you walk along this line and remove everything which has wrong angle. So so I walk along this line and I see, so if I have at least 2 points and the cross product is different, I pop this from the stack. So again, so all of these, so starting from here to here, so this part is just normal Graham algorithm of finding convex hull. That's something you normally store in your library. Okay. That's it. So again, the idea of the problem is very simple. You find some interesting points and then build convex hull of them. That's it. So, okay, and again, the last problem is basically the same. So what's the different in the last problem? What's different in the last problem? they, okay, where is it? Did I remove it? Let's copy it one second. So they don't give me these numbers. They only tell me which cells have 1, 2, or 3. So they give me these cells. So they give me indices of all the cells which can intersect the border. Yeah. So they give you indices of all these cells, and you need to produce again the polygon. Okay, clear enough. It should be clear enough. Okay. How you solve it? No, basically the same way. The same way. I wanna produce the same interesting points, these points. Yeah. And maybe some other points inside. And I do it in the same way. I find the cell on the border, this one, which has 2 zeros connecting to it. Then this point should be inside the polygon. Yeah. So I find all these situations again. Find all these situations. So this point must be here. This point must be here. For this point must be here. This point must be here, and this point must be here. So again, produce all the same points by looking at the cell which has 2 neighbors which are out of the polygon. This one, again, all the same thing. The only difference is you need to check if the point is inside or outside. Yeah, so sometimes you have 0, sometimes you have 4s. Yeah, so you need to kind of distinguish them. And you do it like this. So no, basically all the points inside this region are 4. So all these points should be 4s. Yeah. How to check if point is inside or outside? No, many ways to do it. So I do it like this. For every y coordinate, I remember the leftmost and the rightmost point. So everything in between is inside the polygon. That's it. Everything outside is outside. So that's it. So I will just what I will do. You see. Here. I will take the same code from the problem G, and then just remove this part. Okay, let's no. I already removed it. Okay, so I removed this first part from problem G, which calculates these interesting points. This one, I just removed it, and then I make a new one. So it's already second version. Doesn't matter. So that's what I'm doing here. Okay, let's read the final code. It's just I'm doing when I modify code to make another code, it just looks too messy. Let's look at the final code. So this part is the same. So starting from here, it is the same part. Yeah. So this is the same Graham algorithm. You see. So this is all the same. The only difference is how I build these interesting points. I do it like this. I read all the given points. For every y coordinate, I find the leftmost and rightmost here. And here I check if the point is inside. So if x coordinate is between leftmost and rightmost, that point is inside. Yeah. Now I check all the points on the border, check if it has 2 neighbors outside. Again, it's the same logic as in problem G, actually. Yeah. Then I add this corner to my set of interesting points. That's it. So again, this part changed when part which builds the set of interesting points. And after that, the rest is the same. You just build the convex hull like we did before. No, that's basically, that's problem H. Let's look at your solutions. Okay. Okay, hour and a half to solve problem G. Not bad, not bad. Okay, you grabbed some, I believe you grabbed some geometry. Yes, you grabbed normal convex hull. That's normal approach. Yes, if you already have pre-written convex hull, just use it. Nowadays, almost any contest allows you to have pre-written code, except I don't know, except IOI, I think. Yeah. In ICPC, they allow you to have printed materials, so you can have it printed and just type it from the printed one. Yeah. Um, a little bit too difficult. Yes, it should be easier. Okay, you're kind of doing the same. Yes, so you okay. Too complicated. Okay, this part is too complicated. You can simplify this part easier. But then you build all these points and build a convex hull. Yeah. Okay. Anybody solved problem H? Oh, you solved problem H also. Okay. But again, the difference from G to H is not that much. Okay, you have the same convex hull and just different. Okay. Yeah, I believe that does pretty much what expected. Yes, and here just yeah. You actually simplified the code. Actually, you see your problem H solution is easier than your problem G solution. Nice. So that's it. That's contest 17. You have any more questions? No? Try to solve these problems. Again, if you didn't do it during the contest, okay, you finished 30 minutes. Okay, you have 3-hour contest. You spend more time. It's such okay. You solve problem E. Okay, at least good. So try to solve more problems like this, especially if you feel they're difficult for you. So if you feel you having problems implementing a lot of code, that just means you need to implement more code. You just need to do it more often and learn how to do it fast. Yeah. So after you solve a couple of hundreds problems like this, you just don't think about it. You just implement it because okay, you need to implement this. Okay, here you are. Yeah. And then move to interesting problems, because sometimes you have interesting problems which hidden after some implementation stuff like this. So you just implement this and then move to interesting problem. Have some fun. Okay. Have any more questions? No? We're very fast today. Okay. Okay, if you don't have any questions, then see you next week.